Morning, everybody. Listen, I'll return the exams this afternoon sometime. I'll post the solutions. I'll post it on Google so you can see which questions you missed. But then I'll post the video solution on it too. So sort of thinking forward, where we're going, we have 3 more class days for Blue Group before we have the next exam. I'm just going to do one chapter on that, just chapter 9. And so we'll spend time going through about half of it today, and then the other half on the next class day, and then that last day will be used for review for the test. So it's going to be sort of your lightest exam of the entire semester, which I will do really well on it. Okay? Courtney?
I have a question. So how are you going to figure out like the mini exam grades since we're overall grade? Are you going to average them together, add them together?
They just add together. So everything adds together, and then I divide by 700. So you'll have your quiz average, which is your top 4 quiz grades. That's out of 100. That's, you just add up those points. And then you have 4 exams. That's another 400. And then you have a final, which is cumulative. It's 150. That's 400, 500, 650. And then you have the class participation. So there's a total of 700 points. And then there's an additional 20 points that just sort of goes into the pot, but you divide the entire thing by 700. So if you want to calculate your average, just add up all the points that you have, the exams, the quizzes, or those quizzes, class participation, and the final exam, and then you divide by 700. That's what that grade calculator does, by the way, so you can put in your various scores for those things in that grade calculator. Okay? I just want to say the how to make an A or to make an A, B, C, D thing, that's no longer valid. It doesn't take into account your last exam. So I moved it down to the little track there. You can still see those because, it's valid back before exam 4A. But as of now, it doesn't take into account that. Please?
Is there one more quiz?
Yeah, we'll have another quiz. We'll probably do that next time. What are we? We're blue? No, we're there, but here or here? You'd probably rather have it on the 9th, huh? Let's do it on the 9th and the 11th. We'll do that review, and then we'll do review that day, and then that day in the class we'll do it. That's better, yeah. Okay? I do want to talk a little bit about advising, because we've been talking to students as they move into their classes, especially you pre-meds. So you pre-meds are, if you're biology, you are required to take Chem 435 and Chem 437. That's biochemistry. But I recommend that you talk to your advisor. This is allowed. If you talk to your advisor about instead taking Chem 435 and 436, those are the 2 lectures for biochemistry. And students don't typically do that. I think it's because they view biochemistry as hard. Which, it's hard. If you go to medical school, it's going to be 10 times as hard. Now, that's what Dr. Eubanks at LSU New Orleans says. He says that you take your undergraduate and you multiply it times 10 to get med school. So biochemistry is really, really important for medical school. Your first year of med school is biochemistry. So when you take Biochem 1 next semester, or is that next semester you take it? No, next fall, I think. Most of you are going to take Biochem 1. Have it in mind if you want to take Biochem 2. And even talk to your advisor and say, hey, can I just not take the lab and instead meet your requirement by taking the 2 lectures? Ask your advisor that. I'm pretty sure they'll say yes. Okay, if you're chemistry, they'll absolutely say yes. But if you're biology, I'm pretty sure they'll say yes too. Okay? The lab's useful too. So if you want to take the lab too, that's great. But especially if you pre-med, it's really the 2 lectures that are most important. Is that clear? Okay. It's a hard class. Right? It is a hard class because it's, it's biochemistry. It's not easy. It shouldn't be easy. Right? Being a doctor is not easy. So just be prepared for that. If you want to take both semesters of that class. Yes? Are you going to take both semesters? Yeah. It's very important. I think probably advanced anatomy and biochemistry are the 2 most important classes as you head into medical school, especially for that first year. All right. Let's see, any other questions? Yeah, Megan?
How many questions is the final?
Okay, so the final is about 50-ish questions. It's about twice the length of a regular exam. And the final is cumulative. So if you want to start studying for it now,
I recommend that you start studying for it now. The way that you would study for it, the way that I write the final, is that I take our 4, or what are now 5 exams that we have. I take our 5 exams, and I pull questions from those, and then I sort of change up the questions. Sometimes I'm just changing the numbers. Sometimes I might change the figures, like the whole ranking the moments of inertia. I would give you a different figure, but I would still ask you to rank the moments of inertia. Point is that if you have a question that's not on the exam, some topic or idea that's not on any one of your exams, it won't be on the final. I create the final from your 4 exams or your 5 exams, and but I change every one. So I say that practice from your own exams, but don't memorize them because that won't help you at all. You'll see different problems, but they'll still be like the same stuff, and they'll look really similar. You'll be able to say, "Oh, that was from exam 3, number 25," but now it looks different. Okay? So about 50 questions, 40 to 50, 45 to 50. But you get 2 hours, 150 points, so 4 for an exam. It's really a good place for you to gain back some points.
Is it going to be in person or online?
It's going to be in person. Yes. Very excited. And in fact, Physics 2 next semester is going to be in person. It's going to be normal. There's not going to be any flip class because I know, isn't that crazy? We're going to be in the big class in the Touch auditorium. They have big comfy seats over there. Y'all been over there? It's like a movie theater. Touch auditorium?
Oh, yeah.
Yeah. So as far as right now, anyway, we'll be able to fit everybody in there unless they take time away. They better not. I'm excited. It'll be good. I don't like this semester. Nobody likes this semester, but we're doing okay. We're learning new things. All right. So chapter 9. Some of the things in chapter 9 you've seen. Some of the things are like 3rd grade science, but some of them you probably haven't seen. And the first is phases of matter. I'm going to go through the notes a little bit, but I want you also, don't forget that you need to go through and watch all of chapter 9, because some of the details I won't cover, but you might still see them on the test. So today I want to look at phases of matter, elasticity, density, and pressure. And then the next time I'll look at these other three topics. So phases of matter. You know the phases of matter, right? Solids, liquids, and gas. Be able to identify what those are. There is also a 4th type of matter, and that is a plasma. Plasma is just an ionized gas. It has equal numbers of positive and negative particles. And then there's another type of material. It's not really a phase of matter, but it's called dark matter. And dark matter is a matter that doesn't emit or reflect light. This was discovered, proposed back in the 30s and then again in the 70s. It's a thing. It actually exists. Astronomers have given it the name dark matter just because it appears dark to us, that you can't see it. When you look out in space, there are things that you can see, stars mainly, but there are some things that you can't see, and that's called dark matter. What they did is they looked at galaxies, and they looked at their rotation curves, and the galaxies appear to be rotating a lot faster than they should have been. And they said, well, that's because of all this extra mass that's in there. So it exists. We just don't really know what it is. And so, you know, if you ever discover that, Nobel Prize for you. That would be awesome. Okay? And that might be a Nobel Prize in the next century. So keep your eyes out. There's more about that in the lecture in the screencast. All right. Elastic properties of solids. This has to do with stress and strain. Anytime I talk about stress, that's going to be a force per unit area. So stress equals a force per unit area. And stress will always lead to a strain. And a strain is a deformation, and it's going to be a delta L over L. This is a deformation of the solid. The equation that we use to describe stress and strain is related to the elastic modulus, and that equation looks like this. It is that the stress, F over A, that's a force per unit area, is equal to the elastic modulus, that's called the Young's modulus, times delta L over L. What this says basically is that if I pull on something, and this isn't a good example. And if I pull on something, if I apply a force per unit area, it changes the length. So this rubber band has a certain cross-sectional area. That's our A right here. This is the cross-sectional area. If I apply a force to it, then I go from L, I go to L plus delta L. That's stress and strain. I apply some stress, I cause a deformation in the solid. I can have stress and strain acting in 2 and 3 dimensions as well, and they work very similar to the way we do it here, but we're just going to look at it in 1 dimension. So stress and strain, if I apply a force, it changes the length of that material. Here are some Young's moduli. The Y is the Young's modulus. It's not after me. It's some scientist from 100 years ago. And so that's just the force per unit area for the value Y. Let's try this quick test. I have a tendon in my arm without any pressure on it. It has a length. There's the cross-sectional area, which I gave you conveniently in square meters, which you needed in square meters. And I want to know how much does it stretch when I have a force of 100 newtons applied to it. Just like the rubber band, except now this is a tendon. If I apply that force to it, how much does it stretch? And then I give you the Young's modulus for that.
Can we put the unit of area in meters squared or centimeters squared?
You need everything in SI units so it'd be meters squared, but I actually give you it in meters squared right here, so you specify it.
Yeah, so I was just making sure.
Yeah, everything in SI, and then when you get your delta L, which is what you're looking for, it'll be in meters. You need to convert that into meters. All right, let's try to wrap this up in about 10 seconds. Stop at 2:15, 2:15. Just guess if you're not sure. Looks like you're doing pretty well. All right, good. I think B is right. Let's take a look. So these are mostly just plugging into the equation correctly. So I have my stress, which is a force per unit area. That's going to be equal to Y times delta L over L. And I'm looking for how much does this thing stretch. That's going to be looking for delta L. So I solve this for delta L, multiplying both sides by L over Y. So I get F over A, L over Y. My force is 100 divided by my area times L, which is 0.1 meters, over Y, which is 2 times 10 to the 7th. Pascals, that's a Newton per square meter, that's the unit. And I get I get 0.007 meters, is that right? When I do that? Yeah, so I get 0.007 meters, and that's going to be 0.7 centimeters. All right. So mostly these are just reading it and knowing what the different variables are and being able to apply them correctly. But you'll see one like this on the exam. You'll see it on the quiz next week too, or whenever we have that quiz. All right, let's look at density and pressure. You have a lab on density and pressure this week. It's posted. Yeah, that lab is due on the 11th. Anyway, density is our Greek letter rho, and it's measure mass over volume. You've learned this. You should know this anyway, how to find density. So for example, the density of water is 1,000 kilograms per cubic meter. That's a good number just to know, that in 1 cubic meter of water, that's a mass of 1,000 kilograms. By the way, this is also equal to a gram per cubic centimeter. That in just 1 little cubic centimeter of water, that's equal to a gram. You might ask the question, you know, why is the density of water 1, or why is it 1,000? Have you ever thought about that? Why is the density of water 1? No? Doesn't that seem fortuitous, huh?
Because it's the standard for use of measurement.
Yeah, it used to be the standard, right? Remember we talked about the standard for mass? The standard for mass now is this watt balance. But in the very beginning of standards, we didn't talk about this, but in the very beginning, it was based on the density of water. That a kilogram was defined by the mass of 1 cubic, or rather, 1,000 of a cubic meter of water. So that's why it's equal to 1, because it was the standard that we just set it that way. Here's some densities of substances. It's really useful to know the densities of substances, because then you can identify them based, if you have an unknown material, you can identify it based on the density of that material. Oh, we'll just say that if you notice, this is sort of unique to water, that the density of ice is smaller than the density of the liquid, which isn't normal. That usually the solid is actually more dense than the liquid. And so, of course, that makes ice, because it's less dense than it does what when you put it in water. It floats, right. And so if it didn't float, that is, if as water froze, if it sunk to the bottom, then that would mean that you would get ice sheet on top, and it would go down, and you get another ice sheet, and go down, go down, go down. And then the entire planet would be ice, like frozen ball. So we're grateful for that ice floats. I'm grateful. Otherwise, you know, wouldn't be here, likely. All right, let's try this. What can you say about the density of this block? This block of unknown density floating in a fluid, such as in this figure, which of these statements is true? All right, let's stop at 35. 35. All right, awesome. That was an easy one, right? Hey, what did the dog say after a long day of work? Rough. Okay, so here, if this object is floating, that means that the block is less dense than the fluid. We'll see that next time when we get into Archimedes' principle, why things float, and we'll learn about how to calculate buoyant forces. All right, so pressure. Pressure is equal to force per unit area. I draw my P with a little base on it. That's just to differentiate it between rho. Let me just draw those. So this is my P right here, and this is the letter rho. So the P on the left is for pressure. On the right, that's rho for density. They look a lot the same, but it will help you just to differentiate them in your mind so that you don't get them mixed up, pressure and density. Pressure, the unit is the Pascal, and 1 Pascal is equal to 1 Newton per square meter. So that is pressure. And then also we use the unit of atmospheres. And the atmospheric at sea level is 1 atmosphere. And 1 atmosphere is equivalent to about 100,000 newtons per square meter. So within an area of 1 square meter, like the tiles on the floor, there is a force of 100,000 newtons. Because you have this column of gas, you see the column of gas? It sits on top of this square, and it goes all the way up to space. And so that whole column of gas just sits on top of this 1 meter square area and exerts a force of 100,000 newtons. That's really a big force, because it's a lot of gas. It goes all the way up to space. And this, the whole weight of that presses down. We experience that too, that we feel atmospheric pressure all over us. But because I have a pressure here and a pressure here, the overall net force of that is 0. So we don't experience it in the same way. All right. We can calculate the pressure at a certain depth. And you do this in the lab. There's an experiment where you figure out what is the pressure at a certain depth. Actually, let me go back, because I don't talk about this here, but it comes up in the lab, and you might see it also. And that's the difference between gauge pressure and absolute pressure. Absolute pressure is equal to gauge pressure plus atmospheric pressure. So if you think about your tire, say you have a tire, if I go and I measure the pressure in that tire, I have a pressure gauge, I read the pressure to be about 35 pounds per square inch. But I just told you that the atmospheric pressure is really quite a lot more than 35 psi. And so the gauge pressure is going to be the absolute pressure minus the atmospheric pressure. That in fact, the air inside of your tires are 35 psi above and beyond the atmospheric pressure. So if you want to figure out the absolute pressure in your tires, you would just add atmospheric pressure at 100,000 newtons per square meter to what you measure in the tire, which is 35 psi. Okay? So it's just the sum of gauge and atmospheric pressure is absolute pressure. And in the lab, this online lab that you're doing, you have this experiment, this simulation, where you're looking at a liquid, and you have certain levels within that liquid, and you're measuring the pressure. If you want to know the atmospheric pressure, you just come up here above, and you measure the pressure above the surface of the liquid. And then as you go down, the pressure increases. Okay? All right. So gauge and absolute pressure are related in that way. Now, we can calculate the pressure at a certain depth. In short, the equation for this is going to be equal to the pressure at a certain depth is going to be equal to rho times G times H. Let me show you the derivation for this, because it's not that complicated. If I have a point here, some depth below the surface of a liquid, I have this column of liquid that sits on top of that. Just like there's a column of gas that sits on top of these 1 square meter tiles that extends all the way up to space, I also have this column of water, or liquid, whatever it is, that sits on top of this. And so the pressure is going to be equal to the weight of that column divided by the area of the top of this, wherever this point is. I have like a little cube drawn there, and you imagine that the top of that cube has a surface area A. So this cube, a face of it, has a surface area A. So that force weight is equal to M times G divided by A. But because rho is equal to M divided by V, I can substitute M equal to rho times V. So this would be rho times V times G divided by A. In general, if I have a three-dimensional object and I want to find its volume, what I do is I multiply its area times its length. I'm going to call it its height. And the volume is equal to area times height. right? The volume of a cylinder is pi r squared. That's the area of the face times the length. So it's going to be pi r squared h. So I can substitute that here, and I get P equals rho AHG divided by A. And then these A's cancel, and I get this equation for rho, or for P rather. Okay? But I also have to consider that there is also an atmospheric pressure, P naught. I'm going to call it 1 atmosphere. Say you're at sea level. And so the pressure then, right here, will be P equals to P naught plus rho GH. All right, you don't need to know how to derive it, but I do need you to know that the pressure at a certain depth in a liquid is just equal to the weight of that material that's bearing down at that point. The weight divided by the area of like an imaginary surface. All right, let's try this next clicker question. I have this bubble below the surface of a liquid, and I want to know what is the air pressure or the pressure inside that bubble if it's 9 meters below the surface of the liquid.
Are we going to assume the absolute value of the distance, or are we going to do like -9?
Oh no, you'll never use a negative. It's always just going to be the height. Be careful with your units. You'll need to convert things to SI units and then convert that to atmospheres, or rather you'll need to convert to atmospheres when you get down to the bottom. And then also don't forget about your atmospheric pressure, that you will need to include that. So if I say that you have to include the atmospheric pressure, which answer can you rule out right away?
0.9.
Right, I can get rid of 0.9. I don't know why we put that. But I can get rid of 0.9 because I know that I have 1 atmospheric pressure right here, and that's pushing down on the surface of the water. So I know that my pressure here has to be bigger than 1 atmosphere. Okay, let's stop at 235. 235, just a few more seconds, just guess if you're not sure. Okay, A is right. A lot of you did have B, and you're on the right track if you put B, because what you did if you got B is that you said that P is equal to rho times G times H. I think this is what you did. And then if I calculate this, it's 1,000. That's the density of water times 10 times H, which is 9 meters, and so that's 90,000 newtons per square meter, which is equivalent to, since 1 atmosphere equals 100,000 newtons per square meter, 100,000 pascals, this is equivalent to 0.9 atmospheres. Okay, So if you put B at first, you are on the right track. But what you were forgetting is that you need to include also this P naught term. So I have this P naught, where P naught is the atmospheric pressure, or 100,000 newtons per square meter. And so instead of having 0.9 atmospheres, this is going to be 1.9 atmospheres. So A is the right answer there. Okay? Is that what y'all did if you put 0.9 at first?
I think that's what you did.
All right. Let's go to the chapter homework. We'll work a couple problems, then we'll go back into the, actually, no, I'm sorry. No. Let's do, let's go ahead and do Pascal's principle. I think the others are going to take up more time. We'll do those next time. Okay, so Pascal's principle says that a change in pressure is felt at every point within a fluid. In an incompressible fluid. So if I have a piston like this, where I'm pushing down with some force per unit area, what Pascal's principle says is that that force per unit area is felt all the way throughout the material, that it pushes on every side of the container with equal pressure. This is important that it's an incompressible fluid, because if I have an incompressible fluid, that means that it maintains a constant density. That's what incompressible means. It doesn't change its volume, and so it's able to convey that pressure to every point in the container. When we talk about fluids, fluids include anything that flows, and anything that flows includes gases and liquids. But incompressible fluids, are gases incompressible? No, of course not. You can compress a gas a lot, but liquids are almost all incompressible. Water is incompressible, oil is incompressible. If you have a hydraulic system, which utilizes Pascal's principle, what kind of fluid do you use in that? Do you use water? No, you don't. You use hydraulic fluid, which is an oil-based thing. But you could use water in a hydraulic system. It's just oil is better if it's hydraulic fluid that's used for various reasons, rusting and the like. Okay, so big application of this is in a car lift or in any kind of hydraulic lift. If it's a lift that you're trying to use a person to lift or whatever, a hydraulic lift. And it just says that any pressure P1, which is F1 over A1, is going to be felt throughout. So it would be equal to P2, which is F2 over A2. So if P1 is equal to P2, that means that F1 over A1 is equal to F2 over A2. So, for example, if I have a small area, or if I go from this piston over to this piston, where my area gets big, then I'm also going to have a bigger force. So I can put in a small force with a small area and get out a big force over a big area. And that ratio or that equation is still going to hold true. This will still hold true. If A is big, that means that F will be big. Or if A is small, A is small, that means that F will be small as well. Okay? Let's go to the back of the chapter. We'll work through a couple of problems, and then we'll go to the test in the back and do some more practice. We'll look at some of the conceptual questions too. Okay, let's look at number 2 here. This is a barometer. Next time we'll talk about what a barometer is, but this is a good application. We'll see it in terms of pressure at a certain height. So a barometer is just a tube that's turned upside down, has a vacuum inside of it here, and by the height of the barometer, you can measure the pressure that's pushing down. So I have this atmospheric pressure that's pushing down onto the surface of the liquid, and that atmospheric pressure is pushing this liquid up into that tube. This is asking what would the height of the column be for normal atmospheric pressure. So Blaise Pascal, who says he duplicated this barometer, but first sort of defined how we could use the barometer. He used wine instead of what's usually used in a barometer. Do you know?
Mercury.
Mercury. Do you know why we use mercury? Because mercury is not really the best thing to use. It's toxic for one. So if we
Really sensitive to heat and it's in room temperature, it's still liquid.
okay, yeah, that's maybe so, but that's not really the reason. Why is that?
It's dense.
It's really, really dense. Yeah. So we'll see here that if I have a barometer with this density, that the height of it is really quite big. It's too overwhelming. So I know that P is equal to P naught plus rho GH. And so here I'm looking for what is the height if my P is equal to P naught. So really what I'm doing here is I'm saying that P naught is equal to rho GH. That is that my P naught here is pushing this column up, and I want to know what pressure that is that causes that height. So that's going to be 1 atmosphere is equal to 984. That's my density times 10 times the height. And I'm trying to figure out what the height is. Atmospheres aren't SI units. I'm going to convert that to SI units. 100,000 newtons per square meter equals 9840 times H. And I solve that for H. And that's equal to 10.2 meters. So this barometer that Pascal built had a height of 10.2 meters. So that's the total height of that barometer. Whereas, you know, a mercury barometer, do you know what the height of a mercury barometer is at 1 atmosphere? It's really small. It's 7.6 centimeters. It's about that big. 760 millimeters. You've heard that. That's atmospheric pressure. That's the height of that column at 1 atmosphere. Okay, let's try this one. This is number 6. So this is a piston system, a hydraulic system, and I have a small force on a small cross-sectional area and a big force on a big cross-sectional area. And I want to know if let's look at B. If the piston diameters are 3.8 centimeters and 53 centimeters, so the diameter here is 3.8, the diameter here is 53, and I want to know what force must be given here in order to give me a force here of 20,000 newtons. So I can say F over A is equal to F over A. That's just saying that the pressure on one side is equal to the pressure on the other side. And I'm looking for little f is going to be F over little a times A. That's going to be 20,000 times the area, which is pi times 3.8 divided by 2 squared, divided by pi times 53 divided by 2 squared. I can cancel out some things. I can cancel out my pi's. I can get rid of these 2's too. It turns out they're not really important because they cancel out. And then I can figure out what is that little force. See, I get 102 newtons. Let's say 102 newtons. So in order to get 20,000 newtons over here, you only need 100 newtons over here. It allows you to lift things that are really big. Have you thought about how does this not violate the conservation of energy? Because it doesn't really seem right that I'm putting in a little bitty force and getting out a really big force. And yet I know that energy has to be conserved. I can't just create energy out of nothing. So how does that dive then if I think about the conservation of energy? How am I not, or how am I conserving energy in this? How do I put in a little force and get out a big force? I think about the displacement. Very good. So do I have a small or big displacement on this side? Small or big displacement? That is, how much does this piston move? Does it move a little or a lot? It moves a lot. And over here, I just get a little bit. Have you ever used a car jack, like a hydraulic car jack? You want to lift the car, you just want to lift it a couple of inches. But you have to move that handle through about 50 times back and forth. So over on this side, I have a really small force with a really big displacement. And then on the other side, I get a really big force with just a really small displacement. Remember, force times displacement, that's our work, right? And so I have the same amount of work being done on either side. It's just I'm applying a small force over a big displacement, and I'm getting a big force over a small displacement. So work is still conserved, energy is still conserved. All right, let's try this number 7. This is Young's modulus, or stress and strain. Remember, F over A is equal to Y times delta L over L. So here we're looking for Y. That's going to be F times L over A times delta L. I just multiplied both sides by delta L over delta L. And so that's going to be, this is a rope that's holding up a climber who has a weight of 900 newtons. The length of the rope is 50 meters. The rope elongates by 1.6 meters, so it stretches out that long. And the cross-sectional area, well, A is pi r squared. Excuse me. A is pi r squared. So that's pi times 1 centimeter, which is 0.01 meters. That's the diameter. So I'll take half of it squared. And then that'll give me my Young's modulus for that rope. I get 3.6 times 10 to the 8th. That's in newtons per square meter. Is that what y'all got? 3.6 times 10 to the 8th? Yeah. Okay, good. You'll see questions like these. You'll see questions very, very similar to these. So if you're doing okay on these, if you know how to do these, you'll be fine for the exam. All right. I think that's almost all. We'll come back to this. Let's go to the back of the book and look at some of the old tests. These are going to be all exams 4 as you're looking at old exams. Oh, let's see. This is exam 4 from fall 18. So let's look at exam 4, fall 18. And remember, as you're preparing for the quiz in 2 class periods, not this next time, but the next time, keep practicing with the exam. Some of you still need a good perfect score. Some of you already have 100% quiz average. That's great. If you want to take this quiz, small part, it's probably good practice. But you don't have to, because you already maxed out your quiz average. So some of you really need another perfect score in your quiz. Print out all those old exams, practice out these questions, do it without help. Okay, that'll really help you, because as you make mistakes, you'll learn more about those mistakes. All right, let's look at fall 18. Let's look at number 23 here. Number 23 has to do with density. which fills a larger volume, 100 kilograms of gold or 100 kilograms of lead? You can look at your equation sheet. You have an equation sheet. You have a table with the densities of all these materials. So you'll need to use that to ask, what are the densities of gold and lead? Your equation sheet's in the front or the back? It's in the very front. All right, let's try to stop at 125. 125, so 15 seconds. Guess if you're not sure. All right. Okay, so which of these has the bigger density, gold or lead? Gold has a bigger density? Okay, so the density of gold, AU, right, is bigger than the density of lead. If the question was which takes up more space or which fills a larger volume, 100 kilograms of gold or 100 kilograms of cotton balls, what would be the answer? The cotton balls, they take up a lot more space because their density is less. And so whichever of these has the lower density is the one that's going to take up more space. Density, remember, is mass over volume. And so if I have a smaller density, that means that I have a bigger volume. So the one with the smaller density fills the larger volume. So B is the right answer there. Let's try number 27. Number 27. I'll stop at 35, 35. Okay, remember we said that among fluids, all fluids are materials that flow, that's liquids or gases. Those that are compressible are gases, and those that are incompressible are liquids, right? All liquids are incompressible. So if I'm looking for a compressible material, that's going to be 3 only, so just the gas. Solids are also not compressible. They're like liquids. All right, so C is the right answer. Okay, these are other topics. Let's go down to the next exam, or up to the next exam, fall 17. Let's try this number 17. This is a hydraulic lift. I don't know what force is required to lift a car with a mass of 1,000 kilograms. This is fall 17 exam, is that what I said? Is that right? Okay. So what is F1 required to lift this car? right, let's stop at 130. 130. Okay, good. C is right. So to do this, you say P1 is equal to P2. That is F1 over A1 equals F2 over A2. That's going to be F1 over 0.01 is equal to F2. That's going to be the weight of this car, which is 10,000 newtons, divided by A2, which is 1.2 square meters. If I solve that for F1, was it 83? That was the right answer? Yeah, F1 is equal to 83 newtons. All right. So we'll cover the rest of those topics about the flow of fluids and Archimedes principle next time. Those are a little more involved than what we've done today. So make sure you're here. We'll cover those, we'll practice them. And then on that next class period, we'll have a quiz on this chapter and we'll just review. We're almost to the end and we're sort of going downhill now, but don't coach. We need some of it, we really need to keep pushing. It's on the syllabus. Let me see. I think it should be green on Monday. Yeah, y'all come back on Wednesday. If you ever have any